So BigchainDB 2.0 is coming out. The plan is to release it, the stable version, sometime in June of this year. But we've already done 2 beta alpha releases in April, and we're going to be doing a 3rd alpha release tomorrow, actually. And then there'll be a couple of beta release candidates, and then finally BigchainDB 2.0 final stable sometime in June, hopefully. And so there are many big changes in BigchainDB 2.0, and so I'm going to walk you through what those are. And there's also some very small changes too, and I'll probably mention a few of those, and then point you to some blog posts and things that you can look at to get more details. So just to review at the very high level, what is BigchainDB, for those of you who maybe aren't familiar with it. At a very high level, you can think of it as kind of this weird hybrid thing, software that's some kind of combination of, has some blockchain characteristics and it has some database characteristics. And so some of the blockchain characteristics, it's decentralized, meaning there's no single owner, there's no single point of control, there's no single point of failure. There's all these nodes that are owned and operated by different people, and they all communicate by the same protocol. And so that's what decentralized means. It can do querying, so that's a database property. So you can actually in BigchainDB 2.0, you can use the full power of the MongoDB query engine to do any kind of MongoDB query of the stored data in the BigchainDB database. So you're no longer restricted by a very small set of HTTP requests or something. I'll talk about that more a bit later. Another blockchain characteristic is immutability, which basically means that once the data is stored in this network, it can't be changed and it can't be erased. It's just there forever. So you can trust that if it's there now, it hasn't been changed at all. You can trust that it hasn't been tampered with. And so that gives you greater trust in the data. And then another characteristic, which is kind of something that's both a database characteristic and a blockchain characteristic, is this ability to store records of transfers and of assets and registrations of assets. And it uses some blockchain techniques to do that. So the only person who can transfer an asset is the person who has the private key, the cryptographic private key. And so not even the person operating a node, or there is no administrator of the database, but none of those people can do anything. Like only the people who have the keys can actually control the flow of assets. Okay, so that's just a quick review of what BigchainDB is. Now let's get into what BigchainDB 2.0 is. Okay, so this is actually kind of a high-level picture of what BigchainDB 1.3 was doing sort of behind the scenes. Just to give you, this is just a kind of contrast with what BigchainDB 2.0 is on the inside. So fundamentally, inside of BigchainDB 1.3 and all the previous versions, all of the communication between the nodes was done using database protocols. So if you were using MongoDB, then all of the synchronization and updates was done using MongoDB wire protocol. And if you're using RethinkDB, then the same story, it would be using RethinkDB wire protocol. And what that means is there's basically only one logical database and only one logical database administrator. And there's also a primary. So one of the nodes would be a primary node. And it's just kind of chosen arbitrarily, but it could be that node or that node system administrator is basically very powerful. And they could be the primary for a very long time. Like it doesn't rotate every step or something. They could be the primary for a long time, like days or weeks. And then all the other nodes are secondaries. And what that means is that when you write new data to the database, it gets routed to the primary first, and then the primary writes, and then it all gets replicated to the secondaries. And then reads are usually done by routing them through the primary. You can change a setting usually to also do reads from secondaries. And And so that's how replication was done in BigchainDB 1.3 and all the previous versions. In BigchainDB 2, that's all changed. So I'm going to get to this in a minute. But at a very high level, the communication between the nodes now, between nodes in BigchainDB 2.0 network, is all done by a Tendermint protocol. And there's no sort of single global, single logical database anymore. Every node has its own local database. And then all of those databases are kept synchronized with each other using Tendermint protocols so that they all agree. And even if some of the nodes fail in arbitrary ways, they'll still agree up to a certain number of failures. So I'll talk about this picture in detail in a few more minutes, but I kind of want to go back to explain some high-level concepts of how this all works. So first of all, I just thought I'd do a quick review of what a finite state machine is. It's basically, you can think of a finite state machine as it's basically a computer, but it only has like a very small number of states, like maybe 5 states, or it could have like a billion states, but there's only a finite number of them. So here I illustrated the states by these 5 circles. And so the machine at any given point in time, it's just in one of these states. So it might be in the gray state or maybe in the cyan state. And if you want to change the state of this finite state machine, you can send it a transaction or send it a message. If the message is a valid message or a valid transaction, then it will cause a state transition. And so here, for example, if this transaction comes in and it's valid, it can change the state from cyan to gray. And in BigchainDB, for example, this might be a BigchainDB transaction, like a JSON string, and it basically causes the system to jump from one state to another state. And this system is just one of the nodes in the network, okay? So what about all the other nodes? How do you update them? And that's basically the problem of keeping all of them in sync. And actually, that's what Tendermint does. And this general problem in computer science, it's known as the consensus problem. It's the problem of getting all of these separate finite state machines to all be in the same state, even if some of them are failing. So that in most databases they can handle maybe 1 or 2 of them by crashing. So they basically or maybe they just disconnect somehow. Maybe their network connectivity got lost. But there's a harder version of this problem, and that is, what if some of the nodes are still there, they're still operating, but they're not following the protocol? They're just kind of like, maybe they're withholding information, or maybe they're changing the order of transactions. And so those general kind of arbitrary failures are known as Byzantine failures. And so the more general problem is known as the Byzantine fault tolerance problem. And Tendermint can actually solve that problem. So it's quite a tricky problem to solve. And so what it does is it connects these 4 state machines, for example, in this picture, and makes sure that they all agree with each other. And if one of them starts failing, the 3 will still agree, and even though that one is failing and behaving badly. In most of these kinds of systems, they can tolerate up to 1/3 of the nodes going bad, and then if it usually either stops or maybe it punishes the one that went bad. It kind of depends on the algorithm. Okay, so that's the high-level picture of what goes on. Okay, and then in BigchainDB 2.0, so you can see those sort of magenta circles. Those are the 4 nodes or 4 state machines. And inside each of the nodes, there's basically 3 pieces of software. There's MongoDB database. So each one has its own MongoDB database. There's Tendermint core, which is software written by other community, the Tendermint community. And then there's the BigchainDB software. And it does a bunch of things. It, for example, knows how to check a transaction to see if it's valid. It knows how to store data in MongoDB and query the data. It knows how to talk to Tendermint. And so it basically implements the state machine. And then you can also have variations on that. Okay. And you can see that all 4 nodes have basically the same setup. And each one of these nodes in a BigchainDB network, they're owned and operated by a different network operator. Okay. That's actually the biggest change in BigchainDB 2.0, is this change from communications being done by database protocols to communications being done by Tendermint. And so the rest of this talk is mostly about kind of details now. Okay, so we did make some changes to the transaction model. So those are the things that cause the state transitions. So somebody external to the network can send a transaction to the network, to one of the nodes in the network. It's just a JSON string. And we made 3 changes to those transactions since 1.3. We kind of held off in doing too many of them because we wanted to focus on this major big change that I just talked about. And in the future, there'll probably be more changes to the transaction model. So, but for now, the 3 changes are, the first change is very simple. The version number changed from 1.0 to 2.0. That's easy. The second change is, rather than hashing then fulfilling, we fulfill them. Okay, we'll do it. What does that mean? Hashing is used to calculate the ID of a transaction. So a transaction is basically a JSON string, and if you hash everything except for that ID, you'll get a hash, and that is actually the ID of the transaction. And fulfilling is kind of this high-level name that we call the process of satisfying a condition. And a condition is a thing you put on an output so that you can transfer that output. So the most typical kind of fulfillment is the signature fulfillment, where you have to calculate a cryptographic signature. Anyway, the main idea here is that before we would always calculate the ID of the transaction first, where we would just put those signatures as null, and then later we'd calculate the signatures. But now we calculate the signatures first, and later we calculate the ID of the transaction, including those signatures. And I wrote a blog post explaining why we did this. But I don't know if I want to get into all the details right now. You can look at the blog, BigchainDB.com, and find that post if you're interested. And the last major transaction change is that so when we're calculating these cryptographic signatures, before the thing that we would sign would be basically the whole transaction, like everything. And for every input that you're computing a signature on, you would be signing the exact same message. And so there was a bit of a security issue there in that if there were, like basically that cryptographic signature would be the same for some inputs sometimes. But you didn't want, maybe one time you didn't want to spend or transfer both outputs. So now basically what we've done is we made it so that every single input has a different message to sign, and that makes it so that all of those signatures are going to be different. So it's a bit more secure. And so and the details of that are also explained in that blog post that I mentioned earlier. So we've updated all of the drivers so that you can construct transactions in Python or in JavaScript, and it just does this for you. You don't have to know about how this all works. It's just kind of behind the scenes. Okay, so that's changes to the transaction model. We also made some changes to the HTTP API. So if you want to send a transaction into the network, you basically send a HTTP post request to one of the nodes using this transactions endpoint. And that was changed ever so slightly. We've added this new mode parameter. So now rather than just having one kind of way of doing this, there's now 3 different ways to post a transaction to a network. One of them, this async way, is the same as before. So what that basically means is if you send a transaction to the network, it'll respond immediately saying, yep, got the transaction, I'm processing it. I don't know what happened to it after that, but I got it. Then there's the sync mode, which is basically send it in and it'll validate the transaction, and if the transaction is valid or invalid, it'll tell you. but it doesn't if it ever got written to the blockchain. And then the third mode is commit. That one won't actually get back to you unless the transaction actually gets recorded, like committed to the blockchain. And if you just don't include the mode query string at the end here, like after the question mark, and you just do the top line, that'll still work. It'll just default to the async, which is the way it always was before. So all of your existing code will continue to work like it did before. So that's okay. So change number 2 is a very trivial one. It's just a change in a name, and also a value. So if you want to get a particular block from the blockchain, before you'd use this blocks endpoint, and you'd give the ID of the block, which would be a hash. You just give the block height, which is an integer. So big long hash, you just specify an integer like 123 or something. And the block at height 123. And then what'll come back now is what's inside the block. And before it'd be quite complicated. It would have every single transaction in there in this list of transactions. It'd also have the timestamp and an ID, which is a hash, and a signature. But now all that comes back is the height and the list of transactions. It's actually a bit different than what's stored in the Tendermint side. And we might add more to this, but this is what comes back for now. And then the fourth change, we've gotten rid of a few endpoints. So the status endpoints are now gone because you can basically get that same information using those new ways of posting, like the sync way or the commit. And also there's no endpoint to get the votes anymore because the votes are all handled by Tendermint. We might add that endpoint back in the future, but for now it's not there. And I think this is the last, so the last change to the HTTP API is there is a new endpoint to get the current list of validators, which is kind of like the public keys of the voting nodes as of right now. And that list might actually vary from node to node, but they usually agree with each other, and that's the list of everybody in the network. Okay, so that's kind of technical changes. This is a very high-level change. So before in BigchainDB 1.3 and all the previous versions, going back to like 0.10 or something like that, we supported both MongoDB and RethinkDB. And here's some graphs showing you the commit history to those MongoDB and RethinkDB. They both ended more or less like a few days ago. And RethinkDB goes back to 2010 because that's when the project started roughly. MongoDB goes back to about 2008. But you can get a high-level sense of what's kind of going on in the community or with these projects. You can see that MongoDB, there's kind of steady progress and lots of commits going on, no incredible increases or no incredible decreases. But with RethinkDB, something happened, in late 2016, apparently. And if you know the backstory there, basically the company behind RethinkDB, the company got acquired by, I forget who, but anyway, RethinkDB, the company ceased to exist, and so there was nobody working full-time on it anymore. And so it still exists as an open source project, but it's kind of, withering. Meanwhile, MongoDB has become a public company, and it's one of the most popular databases in the world. So all of this, we basically decided to just support MongoDB for now. And in the future, we might add support for other databases. We still have this database abstraction layer. So for example, in the future, it would be very easy for us to add support for another database. But anyway, that's what we're doing. And so that has some implications for the command line interface. So for example, before when you ran BigchainDB, and to configure it, for example, create a config file, you could specify the backend database, and it would create the config file. Now the only option is a local MongoDB database. You can't have separate one for RethinkDB or for MongoDB. And then there's a bunch of command line subcommands that are very specific to MongoDB or to RethinkDB. So for example, with RethinkDB, it's actually really easy to increase or decrease the number of shards at runtime. That's one of the real cool things about RethinkDB. But that's not really something you want to even do now with the way BigchainDB is set. Now every own local MongoDB database. So yes, you can there, but most people aren't going to be doing that anytime soon because that's kind of a scaling thing you want to do later on. In any case, so these are all gone as well. And there's a new endpoint actually to add a validator at runtime. So when you start a whole new network, you can set up, say, maybe 4 nodes or 7 nodes or 10 nodes right off at the start. But then later on, if you want to add nodes or remove nodes or change their voting power, you can use this command on one of the nodes, and that'll change that on that node. And then at least 2/3 of the other nodes in the network have to do this. And once they do, and once enough of them agree, then that new node will be added or removed the list of validators. So the options, it's basically BigchainDB upsert validator. You give the public key of the node, and then the power. If you want to get rid of the node, you'd set that to 0. If you want to increase their power, you just increase it to a higher value. And this is also how you'd add a new one. So you just put a new public key there with a power that's not 0, and that's how you'd add a new one. So it's kind of a multi-purpose command. Okay, and then other recent changes. So we changed the license on the code from AGPL version 3 to Apache version 2. And the main difference between those, I mean, there's differences, but the main one is that Apache is it's not a copyleft license, so you can, they can make a code based on Apache licensed code and make it proprietary. Or they don't have changes back with the community. And then a second change that we made is that we've kind of opened up and we've changed the process for contributing to BigchainDB. So now, if you want to add code, you can, that's documented in our documentation. You can create a BigchainDB enhancement proposal, and you can submit a pull request, and we have a whole process for merging those very quickly and iterating. Than before to basically add code and make changes. Okay, so that's everything. Is there any questions? Maybe I'll just pass it.
You said you changed the signature algorithm just for the validators or dual transactions?
Well, the signature algorithm itself is still the ED25519 signature scheme. That's on the transactions. That's actually also what Tendermint uses, just by coincidence. We changed what gets signed. So that's the main change inside the transaction. So before we would sign the whole transaction when calculating those signatures on each of the inputs. Whereas now we kind of take a hash of everything outside of the inputs, and then some input specific stuff gets concatenated on there, and then we sign that for that specific input. So basically each input has a different signature now, rather than some of them before could have the same signature.
So it's not deterministic anymore, it's probabilistic, yeah? And the randomness you send along unsigned, right? I mean, this sounds like a private signature protocol you design, right? With some randomness on top.
No, so we actually have a specification which explains like exactly how you would calculate a signature from of all the pieces in a transaction. And it's actually documented in one of those BigchainDB enhancement proposals, number 13. So it's, it specifies in detail exactly how you'd calculate these signatures, and they're deterministic. So like if I give you a transaction before it's been signed, everybody's going to get exactly the same signature. Yeah.
So what's the performance in terms of transaction amount per second, or like everybody wondering nowadays?
Yeah. Yes, we also wonder that. So we changed from using MongoDB as the consensus and networking layer to Tendermint, and so that's kind of like the main determinant of that. And we've only just in the last month here kind of got that finished, and so we've started doing some tests internally of how fast things are. But I don't know if we have any results to share yet. What I do know is that the Tendermint team themselves have done tests with their own big. We're not the only guys building on Tendermint, right? So there's other Tendermint projects out there, and they've done tests to see like if they have a globally distributed network with nodes all over the world, what kind of transaction rates they can get. And I think they've seen on the order of 10,000 transactions a second for small transactions. So, I mean, it's going to be slower for bigger transactions. So that gives you some sense, I guess, of the order of magnitude anyway.
Could you elaborate on how BigchainDB is now handling, after the switch, the fault tolerance for nodes? You went shortly to other change, and you said like there's about a third misbehaving nodes kind of like allowed. How do you handle fault tolerance in your protocol?
Yeah. So BigchainDB uses Tendermint, like literally, is actual Tendermint code right there inside the node, and so all of the communications between the nodes. So that includes the networking and all the consensus. That's all Tendermint, and it's a typical sort of BFT protocol, which means it can handle up to 1/3 of the nodes, like being Byzantine, having Byzantine faults, which basically means it can be any kind of ridiculous, crazy fault. But any more than that, and what happens, it kind of depends on the protocol. What Tendermint does today, actually, if more than a third go Byzantine, it just halts because it puts a higher priority on consensus or on rather than availability. But this is actually there's other net protocols like Casper, for example, where they put a higher emphasis on availability. Our feeling about this is that if you have a large enough network, say with like 100 nodes or something, and even if you detect that there's maybe 1 or 2 Byzantine nodes, well, you're going to say, well, wait a second here, guys. You guys are like misbehaving, and you're going to take care of them long before you ever get to like the 1/3 problem, So anyway, that's how it works.
Another question, you mentioned the dynamic validator set you introduced right now. Is there some rights management system, and how, in order to, I mean, it could be in a text space as well. And the other question is, do you go back to the Genesis state then and change something? Do you spin up a new blockchain then, so to speak? Or is it a hard fork, some sort of? Because, I mean, this is written in stone, who's the validator and who's not, right?
Well, at any given point in time, every node has a list of validators and their powers. And those actually can differ. Those lists can differ a little bit. But so long as like 2/3 of them agree, like if a particular transaction comes in and 2/3 of them agree, or a block comes in and is voted on, say, by a particular node, that vote will be considered valid if that node considers that validator to be a validator. So it's in its list of validators. And so long as 2/3 of the nodes in the network agree that that validator is in fact in the list of validators, then it'll be considered a valid block. So you can change actually the list of validators and even their powers at runtime. And it's stored locally inside of each node. Yeah, so that's how it works. Other questions? Jimmy?
Do you see any future integrations with graph databases? That would be interesting.
Yeah, so as I mentioned earlier, maybe I'll show the picture here again. Every node contains actually a full MongoDB database. And the operator of that node, whoever they are, they have full access to that database, that MongoDB database. So you can use any API to the MongoDB database. And so MongoDB itself, the MongoDB query engine already provides some graph-like APIs. And then there's third-party software that, for example, you can add a GraphQL API to MongoDB. And so there'd be just like an extra layer that that particular operator could add onto their node and say, hey guys, I'm node number 4 and I'm offering a GraphQL API to my node. You should totally query my node. Or another node, for example, they could add their own special API that maybe handles geolocation queries really nicely. And so everybody, because they have the full access to the MongoDB database, they can kind of expose it as much as they like or as little as they like to the external world. Yeah. Oh, okay. The question is, what size of MongoDB are we talking about? Yeah, so these are, it's basically, it's MongoDB. In theory, that could be as big as MongoDB can get, which is pretty big. But, well, I mean, there's no limit even now. But the actual limits are, it's the cost of adding a new node to the network, really. Because when you do that now, so you have to actually replicate that data to the new node. And, you're going to do that. If you send it over the network, that's going to be pretty expensive. So you probably want to just take a physical copy over there, but MongoDB can grow very, very big. I mean, you can. They're pretty cagey about how big. Certainly into the terabytes. So, yeah. Okay, I'll just go back here.
Who has access to the absurd validator calls, and wouldn't that be an attack vector if you give your own Byzantine nodes enough power as validators?
Yeah, so the upsert validator command is a command line command on the node, each node operator. So there's only 4 node operators here. And only those guys, those node operators, have access to that command line command. The people outside, it's not an external API, it's an internal API. And even if one of the nodes, if they tried to add a node to their list here, it doesn't matter because at least 2/3 of the nodes in the network have to have added it before it even becomes a valid thing, There was a question earlier about rights management. So that's kind of a thing that's built into big blockchain databases kind of at the very granular level. At every transaction output basically has conditions on it which say these conditions must be met if this output is going to get spent or transferred. And those conditions in BigchainDB, they can be pretty elaborate. If you say something like either Joe or Mary has to sign and John has to sign, for example. So it can be like an arbitrary Boolean combination of cryptographic signature conditions. And in the future, we're going to make that even more elaborate, but that's how it works BigchainDB today. Well, I don't want to tie everything up. Maybe we can go to the next speaker.